Hey friends, welcome to the Flutter and Riverpod series. Over 12 lessons, we're going to build a complete e-commerce application from scratch with authentication, a product catalog, a shopping cart, and a full checkout flow talking to a live backend server. So this first lesson has no code at all. Before we write in a single line, we need to understand the problem that state management solves, because if you understand the problem deeply, every tool we reach for later will make perfect sense. So Flutter is Google's open source UI toolkit for building applications from a single codebase that runs natively on iOS, Android, the web, and desktop platforms. You write your app once in a language called Dart, and Flutter compiles it to native code for each platform. Everything you see on screen is called a widget: buttons, text, images, even padding, and they are arranged in a tree structure. Understanding that tree is a key to understanding why state management becomes necessary as your app grows. So here is a simplified view of what a Flutter app looks like as a widget tree. At the top, you have your material app, which contains a scaffold, an up bar, a bottom navigation bar, and so on, each one nested inside the other. Now notice the cart badge widget, that little icon in the up bar that shows how many items are in the cart. Where does it get the cart count from? The cart data might be created deep in a completely different branch of the tree. This is a fundamental tension in Flutter UI. Data lives in one place, but the widgets that need it can be anywhere. State is any piece of data in your application that can change over time. And when it changes, some part of your UI needs to update. We can think of it in three categories. User state. Is someone logged in, and who are they? Data state. The products fetched from your API, the items in the shopping cart, the user's order history. And then we have UI state. Is a loading spinner currently visible? Which bottom tab is selected? Is a dropdown open or closed? All of that is state. The key rule is simple. When state changes, Flutter rebuilds the relevant parts of the screen. One of the first questions you need to ask about any piece of state is, who owns it? Local state belongs to a single widget and never needs to leave. A text field's current value, whether a dropdown is open or closed. Then we have shared state. Shared state is needed by a few widgets that are close together in the tree. You handle this by lifting state up to a common ancestor. But global state is needed everywhere. The user's login session, the shopping cart count, the user's preferences. This is where Riverpod comes in. It gives us a clean way to define state that any widget in the entire app can access. Now, without a state management solution, the typical approach is to pass data down through the widget tree as constructor arguments, a pattern called prop drilling. Imagine your shopping cart count lives at the top of the app, but the cart badge widget that displays it is 4 or 5 levels deep. So every widget in between has to accept the cart count as a parameter and pass it down, even though those middle widgets have no use for it themselves. If you decide to change the data structure, you're rewriting 5 widgets. This is the exact pain that state management tools exist to solve. Flutter gives you a built-in tool for state management called setState, and it works inside a stateful widget. When you call setState, Flutter marks that widget as dirty and schedules a rebuild. The build method runs again with the new data and the screen updates. So this is perfectly fine for local state, a counter, a toggle, a text field's focus. But the moment two separate widgets need to share that state, you're back to the prop drilling problem. SetState scales to the widget, not to the app itself. So this is why the community builds state management libraries for us. The Flutter ecosystem has a rich set of state management options. At the simplest end is setState, we have covered that. Provider came next. It was a community standard for several years, and it's still widely used. Then came Riverpod, which is what this entire series is about. A complete rethink of provider that fixes its rough edges. Then we have Block, which stands for Business Logic Component. This is the enterprise grade choice. We will cover that in a separate series. There are others like GetX, MobX, Redux. But in 2026, Riverpod and Block are the two tools you will encounter in virtually every professional Flutter code base. So why Riverpod specifically? So we have 6 reasons. It's compile save. Type errors and provider mistakes are caught at compile time, not when your app crashes on someone's phone. You don't need build context to access state, which eliminates an entire class of bugs from provider. It is also testable by default. You can override any provider in tests with zero setup. It also handles its own memory cleanup. And also providers can watch other providers. So your dependency structure is explicit and readable. We'll get to see that. And it was built by the same developer who created provider. So it is a thoughtful evolution, not a rewrite from scratch by a stranger. Here is a core mental model of Riverpod. And once you internalize this diagram, everything else clicks. A provider holds a piece of state, say the shopping cart. Widgets that care about the cart subscribe to that provider by calling ref.watch. When the cart changes, let's say an item is added, removed, or updated, Riverpod automatically notifies every subscribing widget, and only those widgets rebuild. So the widgets that don't care about the cart are completely separate part of the UI. They are untouched, and this is reactive programming. You declare what you depend on, and the framework handles the rest. The app you're building is called ShopWave, a complete e-commerce application. It has 4 core feature areas: authentication with login, session management, and token persistence. A product catalog fetch from a real Serverpod backend via REST API, a shopping cart with add, remove, quantity management, and a live total, and an order checkout flow with history and status tracking. So every lesson adds a new layer to this same code base. By lesson 12, you will have a fully working app that is production quality in its structure and patterns. This is a full ShopWave architecture, and it follows a clean 3-layer pattern. I think I've mentioned this a number of times. So at the top is a UI layer, which we tend to call the presentation layer, our screens and widgets. They display data and respond to user input. Then in the middle is a Riverpod providers layer, which we tend to call the domain layer. This is where all state and business logic lives. The UI reads from providers. Providers never know about the UI. At the bottom is DIO, our HTTP client, which talks to the Serverpod backend via REST API, which we tend to call the data layer. Data flows up from the server, through the providers, into the UI. Actions flow down from the UI, through providers, to the server. Clean, predictable, debuggable. So here's a full roadmap of the series. We start right here at lesson 1 with state and the foundation. Lesson 2 gets our project set up and writes their first real provider. Lessons 3 and 4 go deep on how providers work and how ref works, the conceptual core of Riverpod. Then lesson 5 through 10, we build ShopWave feature by feature: authentication, products, detail screens, the cart, provider composition, and checkout. Then in lesson 11, polishes the app with production quality, error handling, and UX. And lesson 12 wraps everything up with a testing walkthrough and a preview of what comes next. So every lesson builds on the previous one. Whenever you encounter a new piece of state in your app, use this simple decision framework, guys. So first question, does only one widget need this? If yes, keep it local with set state. There's no reason to involve a whole state management library for local state. Second question, is this state needed by a handful of widgets that are close to each other in the tree? If yes, lift it up to the nearest common ancestor. Then third, is it needed by many widgets across the app, or is it inherently global, like auth or cart? That is when you reach for Riverpod. Each tool has its place. Riverpod is not for everything, it's for the state that genuinely needs to be shared. Great, so before we finish this lesson, there's one principle I want you to understand now because it will prevent the most common beginner mistakes in Riverpod. State must be immutable, meaning you never modify an existing state object in place. If your state is a list and you call .add on it, Riverpod is watching for a new reference, a new widget, not changes inside the existing one, okay? So it won't detect the mutation and your UI will silently not update. So the rule is simple, always assign a completely new object to state. We will see exactly what this looks like in code from lesson 8 onwards, but plant that seed now. Never mutate, always replace. Great. Now let's close lesson 1 by defining the vocabulary you'll hear in every lesson going forward. A provider. This is a container that holds state. Provider scope. This is a root widget that must wrap your entire app. It stores all provider state. Then we have consumer widget. This is how you make a widget Riverpod aware, so it replaces stateless widget. Then we have widget ref. This is the object that gives you access to providers inside a widget. Then we have ref.watch method, which subscribes to state and triggers rebuilds. Then we have a sync value. This is how Riverpod wraps a sync data. Then we have a notifier that holds state and the methods to change it. And then we have ref.read, which reads a provider once inside an event handler. So these nine terms are the entire Riverpod vocabulary for beginners. So keep in mind of them and we'll always repeat them within the series. That is everything for lesson 1. We have covered what state is and the 3 types of state, how the widget tree creates a state sharing problem, the evolution from set state to provider to Riverpod, why Riverpod is our tool of choice, the reactive mental model, the ShopWave app we are building, and the vocabulary for the rest of the series. So in lesson 2, we write actual code. We'll create the ShopWave Flutter project, install Riverpod and DIO, wrap our app in provider scope, and write our very fast real provider. See you there. Welcome to lesson 2. Last time we built the conceptual foundation, what state is, who owns it, and why Riverpod is our tool of choice. This lesson is where we write actual code. We're going to create the ShopWave project from scratch, install every dependency we need for the series, understand what provider scope does and why it is non-negotiable, and write our very fast Riverpod provider. By the end of this lesson, you will have a working Flutter app with Riverpod fully integrated and running on your device. Before opening the editor, let's understand every package and why it exists. So Flutter Riverpod. This is the core. Every Riverpod class we'll use lives inside here. DIO is our HTTP client for talking to the Serverpod backend, significantly more capable than the built-in HTTP package with interceptors and structured error handling. Then we have Go Router that handles navigation and lets us protect routes so unauthenticated users can't reach the product catalog. Then we have Shared Preferences that stores small key value data on device. We'll use it for the auth token. The grayed out 2, freeze, and Riverpod generator, they'll come in later lessons when we need them, so don't add them now. Open your terminal and run flutter create ShopWave. This scaffolds the full project with all standard directories and files. Then cd into the project and run flutter pub add with all 4 package names on the same line. Flutter installs them and writes them to pubspec.yum automatically, no manual file editing needed. Once done, run Flutter run and verify the default counter app appears on your device or simulator. That single test confirms our environment is healthy before we write a single line of Riverpod code. The full commands are in the description down below. Before writing any code, let's set up the folder structure. We use a pattern called feature first architecture. So instead of grouping all providers together and all screens together, we'll group by feature. Everything for authentication lives in features, in the features directory in the auth folder. Everything for products in features directory in the products folder. Each feature folder is self-contained. The core folder holds shared infrastructure. Our DIO client and constants live here. Then the models folder holds plain data classes shared across features. Create all these folders now and leave them empty. We'll fill them lesson by lesson. Now open lib in the lib folder main.dat and delete everything, the entire default counter app, all 80 plus lines of it. We're replacing it with a few lines starting point. So two things happen in the new file. First, we import Flutter Riverpod. Second, the single most important line in the entire setup, we wrap our root widget in provider scope. My app stays a plain stateless widget for now. Provider scope sits above it and above material app. So run the app after this change and confirm you see the ShopWave text. The full source code for this file is in the GitHub repo. Great. Provider scope is the widget that physically stores the state of every provider in our app. So think of it as a global registry. When you define a provider and a widget reads from it, provider scope is a container that creates and holds that value. Without it, providers have no storage and Riverpod will throw an error immediately. So 3 rules to remember. It must be the outermost widget, above material app. You have exactly one in a production app. And in test, you can create a fresh provider scope per test case to keep state isolated between tests. So these rules never change throughout the series. Great. So what is a provider? A provider is a container that holds a value and exposes it to any widget that asks for it. So three things make providers different from global variables. They are lazy. The value isn't created until something fast watches the provider. So there's no unnecessary startup work. They are a single source of truth. So every widget watching the same provider gets the identical value, always in sync. And they are managed by the provider scope. The lifecycle, creation, the cleanup are handled automatically. So declaring a provider at the top level of a dat file is all you need. Now let's write our first one now. So create the file do underscore client.dat in our core directory. The provider has 4 parts to understand first. So we have first is final do provider. That's a top level constant outside any class. This is how every Riverpod provider is declared. Second is a builder function, ref. Riverpod calls this exactly once, the first time something watches a provider. Third, we pass our serverpod base URL from app constants, one place to change it for the entire app. Then fourth, we will attach a log interceptor. This prints every HTTP request to our terminal during development. We'll remove it before we ship, obviously. The full source code is in the GitHub repo. Now, the ref parameter is inside a provider is how providers depend on each other. Right now, our DIO provider doesn't use ref. It creates a DIO standalone. But in lesson 5, our auth provider will call ref.watch with DIO provider as an argument to inject the DIO instance. Riverpod ensures only one DIO instance is ever created. Both auth provider and products provider get the same one from provider scope. I hope you're getting to understand the value of provider scope. So if DIO provider were ever invalidated and recreated, every dependent provider would automatically update. So this is dependency injection built into the framework. No setup, no server locator, no boilerplate. This is a real deal. Now, to read from a provider inside a widget, you make exactly 2 changes to a standard Flutter widget. First, you need to extend the consumer widget instead of the stateless widget. Just one word. That opts the widget into Riverpod. Then second, the build method gains a second parameter, which is a widget ref. That ref object is your gateway to every provider in the app. Then inside build, call ref.watch and pass in the DIO provider. This returns the DIO instance and subscribes the widget. If DIO provider were ever recreated again, the widget will rebuild automatically. So 2 changes and the widget is fully Riverpod powered. The full source code is in the GitHub repo. Now Riverpod gives you 4 ways to access providers from widgets. Consumer widget, this is the one you'll use around 80% of the time. It's a drop-in for stateless widget with widget ref added, as we mentioned earlier. Consumer stateful widget paired with consumer state is for when you need lifecycle methods. In consumer state, ref is a class property available everywhere, not just in build. The consumer widget is used inline. You insert it to give just a small section of a large widget tree access to a provider without converting the parent. And plain stateless widget is still fine for purely static display only widgets that never need state. So we'll use all 4 across the series. So this is a rule that trips up every Riverpod beginner at least once, even myself when I started. Ref.watch subscribes your widget to a provider. It rebuilds every time that provider's value changes. So you use it inside build method when you need to display data. Ref.read reads a provider's value exactly once with no subscription and causes no rebuild. So use it inside callbacks button where we have onPressed, onTap, onChange. The mistake to burn into memory is never call ref.watch inside a callback. Riverpod will throw an error because watches are only valid during the build phase. The mental model that makes this easy: watch to display, read to act. So you use the ref.read in places where there is action needed. On tap, on changed, on pressed. Okay, great. Now let's create our constants.dart with an app constants class. The private constructor prevents accidental instantiation, so it's a namespace, not an object. We move our base URL, timeout durations, and storage key strings in here. Now let's update dio_client.dart to reference app constants.base URL instead of the hard-coded string. The immediate benefit is when you want to test against a local Serverpod instance, you change one line in one file and the entire app switches. Either it's staging URL, production URL, token key names, all controlled from a single place. This is a production habit worth building from the very first lesson. Full source code is in the GitHub repo. Now here's a complete picture of what we've built. Provider scope sits at the root in main.dart, the storage layer. Okay. DIO provider declares a DIO instance using app constants for configuration. Home screen is now a consumer widget that calls ref.watch and passes in the DIO provider, gets the DIO instance, and displays the base URL as a sanity check. The grayed out providers on the right, auth, products, cart, orders, are coming in later lessons, but they will all follow this exact same pattern. A provider declared in core or features, a consumer widget reading it via ref.watch. So learn this pattern once, repeat it 12 times. That's the idea that we're going with. So let's run the app with Flutter Run and check 3 things. 1, it compiles and you see ShopWave on screen with no errors. 2, check the terminal for log interceptor output. It fires when home screen watches DIO provider for the first time, confirming the provider was created. Then 3, no provider scope error. If you do see that error, go back to main.dat. Provider scope must wrap material up, not be inside it. So if all 3 are green, lesson 2 is done. You have a working Flutter project with Riverpod integrated, a real DIO provider pulling configuration from app constants, and a consumer widget reading it successfully. Now, 3 mistakes will cost you time if you don't know them now. First, provider scope in the wrong position. It must be above material app, not inside it. I know I've repeated this many times, but it's so easy to make a mistake with this one. Any widget above provider scope cannot access providers, and material app itself wraps a lot of infrastructure. Okay, so the second is providers inside a class or function. Each call creates a new provider object that Riverpod treats as a different provider entirely. Top level constants only, always. Then third, we have ref.watch inside a callback. Riverpod only allows watches during the build phase and will throw a clear error if you call it on places like onPressed, onTapped, or similar actions. All 3 have unmistakable error messages. Now that you know what to look for, each one is fixed in under a minute. Here's everything we accomplished in lesson 2. We set up the ShopWave project with a feature-fast structure that will carry us cleanly to lesson 12. Installed 4 core dependencies and understood why each exists, wrapped the app in provider scope and deeply understood its role, wrote our first real provider, DIO provider, and read it in a consumer widget, internalized the ref.watch versus ref.read rule, created an app constant class for production quality configuration, and verified the app runs with 3 green checks. The foundation is complete. That's lesson 2 complete. In lesson 3, we go deep on provider types, the full map of what Riverpod gives you and when to reach for each one. Today, we use the basic provider for a read-only DIO client, but Riverpod has notifier provider for mutable state with methods. That's our cat and auth. A sync notifier provider for sync data that loads from an API. That's our product list. Stream provider for real-time continuous data, and state provider for simple toggles and counters. We'll build a decision framework so that when you face a new piece of state in ShopWave, you know immediately which provider type to use. See you in lesson 3. Welcome to lesson 3. So in the last lesson, we wrote our first provider, a simple provider holding a DIO instance. But Riverpod has 5 provider types, and choosing the right one is a skill that separates beginners from intermediate. So today we cover all 5, understand what problem each one solves, and build a decision framework you can use instantly. The lesson has no new code to write. It's the mental model lesson. So get this right and every provider from lesson 4 onward will feel obvious. So let's anchor where we are. We know provider scope, right? Provider and consumer widget. But now we need providers for things that behave very differently. The shopping cart needs to change. Items get added and removed. The product list must be fetched async from the server with loading and error states. Auth needs to transition through loading, success, and error. None of these fit the simple provider we used for DIO. That's exactly what this lesson answers. The right provider type for every kind of problem. So here's a complete provider map, a spectrum from simple to complex. So at the simplest end is provider, holds a read-only value that never changes. We already know this one. Next is notifier provider, mutable state with methods used for auth and cat. Then a sync notifier provider has the same idea but for async data from a network call used for products and orders. Then we have stream provider for continuous real-time data and state provider for simple primitives like a boolean toggle or a selected tab. So today we cover all 5 and build a decision framework to always pick correctly. Provider is the simplest type. It holds a value created once and never changes. The lock icon is intentional. Widgets can read it, but nothing can modify it from outside. So think of it as a read-only service container, okay? You've already written one, the DIO provider. Other perfect uses are app configuration that doesn't change at runtime, service or repository objects you want to inject into other providers, and values were derived from other providers. So if you want to modify the value inside a provider, that's a signal you need a different type. Notifier provider is a workhorse of Riverpod. It combines two things: state, the current value, and a notifier class containing methods to change it. So in lesson 8, we build cat notifier with add item method, remove item method, and clear method. So when add item method runs, it updates state. Riverpod detects the change and rebuilds every widget watching the cat. So notice the two directions in the diagram. Widgets watch state to display it and call methods via ref.read to change it. Auth and cat are both notifier providers, the providers you will use most in ShopWave. Great, then we have a sync notifier provider, which is notifier provider's async sibling. The difference is the state is asynchronous, fetched from a network, database, or file. Riverpod wraps the result in an async value with 3 possible states: loading, error, and data. So in your widget, you call .when method and handle each case. You never write if-else chains for async state again. In lesson 6, we build products provider using async notifier provider. The loading state, error handling, and retry logic are handled automatically. It can also have methods. Our order provider will have place order method alongside its async fetch. Now let's see what a sync value actually replaces. Without it, you manually track 3 separate variables: is loading, error message, and products, and write a chain of if-else to decide what to show. If you miss one case, your UI breaks silently, so you can even reach impossible states: is loading true and products not null simultaneously. So with async value, the Dart compiler forces you to handle all 3 states through .when method: provider loading handler, an error handler, and a data handler. Forget one, it won't compile. So this is not just cleaner code, it's safer code. We use this pattern every time we fetch from Serverpod. Stream provider wraps a Dart stream. Every time the stream emits a new event, the provider updates and every watching widget rebuilds automatically. So like async notifier provider, it returns an async value, so you use the same .when method pattern. The key difference from a future gives one value when it's done. A stream emits values continuously. So stream provider manages the subscription automatically. It subscribes when first watched and cancels automatically when no widget is watching anymore. So we won't use this in ShopWave since we're using REST, but it's the right tool for WebSocket and Firebase real-time queries. State provider is the simplest mutable provider. It holds one value, maybe a boolean, an integer, a string, and you update it by setting .state directly. So no notifier class, no method, just ref.read, pass in the notifier, .state, and assign it with a new value. It's perfect for UI state that's simple but needs to be shared across widgets. Which bottom tab is selected, whether a filter is active, the current sort order, such things. So the rule of thumb is if the value is a single primitive with no attached logic, state provider is right. The moment you need conditions or multiple fields, you switch to notifier provider. Now let's map every ShopWave provider to its type. The IO provider uses plain provider, read-only service. Lesson 2 done. Auth provider uses notifier provider. It has login, logout methods that change state, which will be in lesson 5. Products provider uses async notifier provider, which fetches from Serverpod asynchronously with a refresh method. That's lesson 6. Then cat provider uses notifier provider, where we have methods like add item, remove item, clear. That's lesson 8. Then we have order provider that uses async notifier provider, posts to the server and fetches history asynchronously. That's lesson 10. If it's async, use async notifier. If it's synchronous logic, use notifier. If it's static, use provider. So here's the decision framework. 4 questions that always lead to the right provider. First question: does the value ever change? If no, use provider. Second question: if it changes, is it just one single primitive with no logic? If yes, use state provider. Question 3. Does it have complex logic or multiple fields needing methods? If data is synchronous, use notifier provider. Question 4. If the data is async, is it a one-time future? Use a sync notifier provider. Is it a continuous stream? Use stream provider. So run through this tree every time you create a new provider and you'll really make the wrong decision. Great. So every provider type can be combined with the autoDispose modifier. So by default, providers live for the entire app session. Once created, they stay. AutoDispose changes this. When the last widget watching a provider leaves the screen, Riverpod destroys that provider's state and frees the memory. So you write it as a sync notifier provider.autoDispose method or notifier provider and call the autoDispose. So you use autoDispose for screen-specific data like the product detail page, which is a perfect example. So don't use it for app-wide state like auth and cat. Those must survive navigation. We'll apply autoDispose to the product detail provider in lesson 7. The family modifier solves a specific problem. So what if you need the same kind of provider but with different parameters? For example, you want to fetch product details, but each product has a different ID, right? Without family, you'd need a separate provider for every product, which is obviously not practical. So with family, you declare the provider once, then pass a parameter when you watch it by using ref.watch, pass in the product detail provider, and pass in the value or the ID of that product. That will give you a provider instance of product. For example, if you added in the ID 42, it will return or give you a provider instance for product 42. Ref.watch, when you pass it product detail provider, passing in the ID 7, it gives you a completely separate instance for product 7, independently cached, independently fetched. We'll implement this in lesson 7 for the product detail screen to understand more. Here's one of Riverpod's most powerful features: providers watching other providers. So inside a provider's builder, you have ref, and you can call ref.watch on other providers. So this creates a dependency graph. When DIO provider's value changes, anything watching it updates. When auth provider changes, say the user logs in, a token provider derived from it updates, which causes products provider to update its auth header, triggering a fresh fetch all automatically. So in lesson 9, we build this chain explicitly, seeing how the auth token flows into every authenticated API call without passing it manually. This is dependency injection without a service locator. So here's a complete quick reference. Keep this accessible, okay? So provider, any type, read-only, no async, used for DIO and config. Then we have the notifier, uses any type, has methods to change state, synchronous logic, used like for use cases like auth and cat. In our case, a sync notifier provider returns a sync value, has methods, uses futures. In our case, we are going to use it in products and orders. Then we have stream provider, which returns a sync value, no custom methods, uses a continuous stream, and it's useful in use cases like using Firebase real-time or WebSockets. Then we have state provider, which uses single primitive, no methods, sets.state directly and passing in the new value directly. It's used for simple UI state like filter sections. So these 5 cover everything you'll encounter in production Flutter development. I hope it makes sense. That's everything for lesson 3. So we covered the full map of Riverpod's 5 provider types: provider for read-only values, notifier provider for mutable state with logic, async notifier provider for async data, stream provider for real-time streams, and state provider for simple toggles. So we learned async value and the when method pattern. We understand autoDispose and family. We built a 4-question decision framework that you can always use. Take a screenshot of it, guys, and mapped every ShopWave feature to its provider type. So this is a foundation lesson. Everything from lesson 4 now onwards is implementation. Every provider we write will click because you now understand the why behind each type. In lesson 4, we do the deep dive on ref, the object that powers everything in Riverpod. We'll cover every method: ref.watch for subscribing in build, ref.read for one-time access in callbacks, ref.listen for side effects like navigation and snack bars, ref.invalidate for forcing a provider to reset, and ref.refresh for restarting a provider and returning the new value. We'll cover where each method is valid, what breaks when you use the wrong one, and look at real examples from the ShopWave codebase. See you in lesson 4. Welcome to lesson 4, the ref deep dive. Ref is the object that gives you access to every provider in your app. It has 5 methods that each do something different. Get this right and your Riverpod code will be clean and bug-free. Get them wrong and you'll spend hours debugging widgets that don't rebuild, callbacks that crash, or navigation that fires at the wrong time. So this is the most important lesson for day-to-day Riverpod use. We'll go through each method systematically, what it does, when to use it, and what breaks when you use the wrong one. Widget ref is the object that gets passed as a second parameter to every consumer widget's build method, right alongside build context. It is Riverpod's gateway object. Through it, you can read any provider in the entire app, subscribe to changes, react to state transitions, and force providers to reset. Everything Riverpod related in a widget flows through ref. It connects your widget to the provider scope at the root of your app, which is where all provider state lives. 5 methods, that's all there is to it, so let's go through each one. Here are all 5 ref methods at a glance. They split cleanly into groups: the react methods, or the reactive methods, ref.watch and ref.listen. They create an ongoing subscription, so when the provider changes, something automatically happens. The non-reactive methods, ref.read, ref.invalidate, and ref.refresh, they perform a one-shot action and leave no subscription behind. Understanding which group a method belongs to is 80% of knowing when to use it. So let's go through each one in detail, starting with the most important, ref.watch. Ref.watch is a method you'll use most often. It's a core of how Riverpod works. It reads the provider's current value and subscribes the widget to that provider. Whenever the provider's value changes, Riverpod schedules a rebuild of this widget, calling build method again with a new value. So think of it as a live subscription. As long as this widget is on screen, it's listening. So use ref.watch exclusively inside the build method, never inside a button's onPressed, never inside init state, never in a future.then callback. Riverpod enforces this. Calling watch outside build method will throw an error immediately. Now ref.read reads a provider's value exactly once without creating a subscription. That's a non-reactive method. The widget will not rebuild when the provider changes. This is the right choice when you want to perform an action, not display data. The classic pattern is in a buttons onPressed, where you call ref.read, pass in the provider class that you want to communicate with, the notifier provider, and call the method. So the .notify accessor gives you the notifier class, and then you call your method. Ref.read is also the correct choice inside init state, the change dependencies, and any asynchronous callback. So the simple rule is if you're pressing a button or responding to an event, use ref.read. Now let's put watch and read side by side so the distinction is crystal clear. Ref.watch lives in build method, creates a subscription, and the widget rebuilds every time the provider changes. You use it whenever you're displaying data, showing a list of products, showing the cart item count, showing the logged in user's name. Ref.read lives in callbacks, button presses, swipe handlers, form submissions. It reads the value once, performs no subscription, and causes no rebuild. It's a one-shot action. So the mental model that makes this stick: use watch to display, use read to act. Every time you write a ref call, ask yourself, am I displaying something or am I acting on something? Ref.listen is a tool for side effects, things that need to happen in response to a state change, but that don't involve rebuilding the widget. So the classic examples are navigate to the product screen when the login succeeds, or show a snack bar when an order fails, or play a sound when something is added to the cart. So ref.listen is declared inside the build method like ref.watch, but unlike ref.watch, it never causes a rebuild. It gives you a callback with the previous state and the new state so you can check exactly what changed and react accordingly. So you use ref.listen for navigation and UI notifications. Use ref.watch for displaying data. So here's how ref.listen works in practice, specifically for authentication. After the user taps login, auth provider transitions from loading to either authenticated or error. So in your login screen, ref.listen watches this transition. When next is authenticated, you navigate to the product screen. When next is an error, you show a snack bar with the error message. So you use next to handle only the specific states you care about without needing to handle all of them. The callback receives both the previous state and the new state, so you can make decisions based on what changed. The widget itself does not rebuild. The navigation and snack bar happen as clean side effects. Now we have the ref.invalidate that tells Riverpod to discard a provider's current state and rebuild it from scratch. So if something is currently watching that provider, Riverpod destroys the old value, calls the build function again, and any watching widgets go back to their loading state while the new value is computed. Ref.invalidate returns nothing. It is fire and forget. So the classic use case is pull to refresh on your product list, where when the user pulls down, you call ref.invalidate, pass in the provider class, and Riverpod refetches from Serverpod automatically. Serverpod is our current backend in this tutorial. Another important use is when a user logs out, you call ref.invalidate on every provider that holds user-specific data to ensure clean state. Then we have ref.refresh, which is a sibling of ref.invalidate. It does everything invalidate does, but it also returns a provider's new value. For synchronous providers, it returns the value directly. For async providers, it returns a future that you can await. So you'll use ref.refresh less often than ref.invalidate, but it's a right choice when you need to wait for the provider to finish resetting before taking the next action. For example, after a user submits a form that creates a new product, you might call await ref.refresh, passing the provider class to guarantee the list has been refetched before navigating to the updated screen. That's an example. Now, the practical guide to choosing between invalidate and refresh. Default to ref.invalidate because it's simpler, it works for most reset scenarios, and it's efficient because it lets Riverpod schedule the rebuild without blocking your code. You reach for refresh only when you specifically need to wait for the provider to finish and use the new value before doing something else. So in ShopWave, logout uses invalidate to clear multiple providers at once. The retry method on the product list uses invalidate. So if we ever needed to verify a refetch completed before navigating, that's when we would use refresh method. Now this table is the most important reference in this lesson, so keep it open while you write your early Riverpod code. Ref.watch and ref.listen both belong in the build method and inside notifier build methods. They are the only two that create subscriptions. Ref.read, ref.invalidate, and ref.refresh all belong in callbacks and notifier methods, not in build method. So notice that ref.read in build method is marked avoid, not forbidden. Technically it works, but it creates a stale closure bug where the widget never updates. And ref.watch in a callback is simply invalid. Riverpod throws immediately. So learn this table and half your potential bugs disappear before you write them. Great, so the most common Riverpod mistake is using ref.watch inside a callback. We've said that so many times. It looks innocent. You want to get the current cart value when a button is pressed. A Riverpod forbids watches outside the build phase and it throws a clear error. Something like tried to use ref.watch. So the fix is always the same. Replace ref.watch with ref.read in that callback. If you want to call a method on the notifier, chain .notifier onto the read. For example, ref.read, passing the notifier class, .notifier, call the add item method and pass in the product. When in doubt, if you're inside any function that's not build, use ref.read. That's a simple rule you can use. Widget ref isn't only available in widgets. Notifier classes also have access to ref as a class property. You can call ref.watch, ref.read, ref.listen, and ref.invalidate from anywhere inside a notifier, its build method, and all its action methods. So this is how providers depend on each other. In lesson 10, our order notifier will call the ref.watch, passing in the DIO provider to get the DIO client. Ref.read, passing in the auth provider to get the current user's token for the authorization header, and ref.invalidate, passing in the cart provider after a successful order to clear the cart. Providers talking to providers in this case, okay? All through the ref. So there's a subtle but important distinction inside notifier classes. If the notifier's build method ref.watch creates a reactive dependency, for example, if the DIO provider changes, the entire notifier resets and the build method runs again. So this is what you want for dependencies that should trigger full reset. But inside action methods like place order method or add item method, you want ref.read, a one-time snapshot at the moment the action runs. Calling ref.watch in a method doesn't make sense semantically. Methods are actions and not subscriptions. So the rule ref.watch in notifier build method for reactive setup and ref.read in notifier methods for one-time access. So let's see how all the 4 methods will be represented in the ShopWave code as we go on with the lessons. Just a glimpse. First, when it comes to displaying cart items, we'll use ref.watch in the build method where widget rebuilds when cart changes. Second is the add to cart button where we'll use a ref.read in onPressed and which calls the notifier method and there's no rebuild. That is when we're navigating to the product screen after the login is successful. We'll use a ref.listen in build, which fires a callback on state changes and no rebuild is made. Then fourth is pull to refresh on the product screen. We'll use the ref.invalidate in the on-refresh callback. Riverpod refetches automatically and watching widgets go back to their loading state. So these 4 patterns cover the vast majority of ref usage in the ShopWave app and in any production Riverpod app. Here are all the golden rules consolidated. Ref.watch in build to display data and subscribe. Ref.read in callbacks to trigger actions without subscribing. Ref.listen in build for side effects like navigation and snack bars. Ref.invalidate in callbacks to reset a provider, fire and forget. Ref.refresh in callbacks when you need to await the reset result. Never ref.watch in a callback, throws immediately. Never ref.read in build for display, widget won't update. And inside notifier classes, use watch in build for reactive dependencies and use read in methods for one-time access. Print the list, keep it nearby, you'll internalize it within the first week of coding. Great, so lesson 4 is complete. You now know every ref method where each one is valid and the golden rules to follow. And I know I have repeated some concepts again and again just for clarity. In lesson 5, we write our first real feature, the authentication. We'll build auth notifier using the notifier provider, define a sealed state class. I'll tell you what that is with 4 states: initial, loading, authenticated, and error. We wire up the login and logout methods to Serverpod via DIO, persist the auth token using shared preferences so users stay logged in between app launches, and we'll use ref.listen in the login screen to navigate our users to the product screen on success. So every piece of ref knowledge from this lesson gets put to work immediately. See you in lesson 5. Welcome to lesson 5, the first full feature lesson. Everything we've learned so far was conceptual groundwork. Today we write real code that does something real. So we're building authentication for ShopWave, a sealed auth state class with 4 possible states. An auth notifier that calls our Serverpod backend via DIO, token persistence with shared preferences so users stay logged in, and a login screen that uses ref.listen to navigate on success. By the end of this lesson, login and logout are fully working. So here's the full scope of lesson 5, 6 pieces, each building on the last. So we start with the auth state sealed class, the data model that everything else depends on. Then we build the user model to hold users' data from the server. Then auth notifier, the logic layer that calls Serverpod, handles responses and transitions between states. Then token persistence with shared preferences. Then the login screen that displays state and reacts to transitions. And finally, root protection that keeps unauthenticated users off restricted screens. So each piece is small and focused. Together they form a production quality auth flow. Before we write a single line of code, let's know exactly what files we're creating. 5 new files and 1 update. Start by creating all 5 files completely empty inside their correct folders. We'll create fast, then we fill in order. We'll walk through them systematically. User model first, it's the simplest. Then the auth state, then the notifier that uses both. Then the screen that consumes the notifier, then the router that protects the routes. Finally, we'll update main.dat to plug everything together. The full source code for each file is in the GitHub repo link down below. Now the user model is the simplest file in this lesson. It's a plain .dat class with 4 fields and 2 methods. When Serverpod responds to a successful login, it sends back a JSON object with a user's ID, name, email, and a JWT token. So we map that JSON into a user object using from.json method. The token field is the most critical. It is a credential we'll attach to the authorization header of every subsequent API call so Serverpod knows who's making the request. We also add to JSON method because we'll need to serialize this user to persist it in shared preferences. Full source code is in the GitHub. So auth state is a sealed class with 4 variants. Sealed means it can only ever be one of these 4. The compiler enforces that. So initial is the starting state when the app launches and we haven't checked for a saved token yet. Loading appears the moment the user taps login and stays until Serverpod responds. Then authenticated carries the full user object and is what lets the rest of the app know who's logged in. Then we have error that carries a message from the server, either wrong password or user not found, so we can show it in the UI. When you call .when method on an auth state, that forces you to handle all 4 variants. If you miss one, the code won't compile. This diagram shows every possible transition in our auth state machine. So the app starts in initial. When login method is called, whether from initial or from error after a failed attempt, the state moves to loading immediately. A loading spinner appears in the UI instantly. Serverpod then responds with either a 200 OK, which moves us to the authenticated with a user object, or a 401 or network error, which moves us to error with a message string. From authenticated, logout method moves us back to initial and clears the token from storage. So auth notifier's job is to drive every one of these transitions. Auth notifier is a notifier of type auth state. The class has three parts: the build method, which is called once at startup, and it checks shared preferences for a saved token, and if one exists, it restores the session by returning an authenticated state immediately. Then we have the login method that takes email and password, immediately sets state to loading, makes the DIO request to Serverpod or your preferred backend, and transitions to either authenticated or error. Then we have our logout method that deletes the token and returns to initial. So the build method is called once before the first widget renders. We use it to check if the user has a saved session. First, read from shared preferences. Is there a token saved? If not, return initial immediately and the app shows the login screen. If a token exists, we make a quick get request to Serverpod to verify the token is still valid. Tokens can expire. So if it's valid, we return authenticated with a user object and the app skips the login screen entirely, going straight to product screen. If the token is expired or the request fails, we return initial and force a fresh login. So this is what makes the app feel native. Returning users are always taken straight in. The login method follows a clean 5-step sequence. So the very first line before anything async sets state to loading. This is critical. It ensures the spinner appears the instant the user taps the button, giving immediate visual feedback. Then we make the post request to Serverpod for login. If the Serverpod responds with 200 OK, we pass the user object from the JSON, save the token to shared preferences, and set state to authenticated. Riverpod notifies the login screens, ref.listen, do you remember that one in our previous? Which navigates now the user to the product screen. If the request fails, either because of wrong password or network timeout or server error, we catch the DIO exception, extract the error message, and set state to error. The ref.listen fires again and shows a red snack bar. So shared preferences is Flutter's key value storage for simple data. that needs to survive app restarts. I have a tutorial in the channel, I'll link it in the description. It's backed by NS user defaults on iOS and shared preferences on Android, both native platform mechanisms. So we use it to store exactly two things, the JWT token and the user's ID. On a successful login, auth notifier writes both. When build method runs at startup, it reads the token. On logout, it deletes both. The key names come from app constants, token key and user ID key. So they're defined once and used consistently. We never had code strings like auth token directly in the notifier. Login screen is a consumer widget that uses all three ref buttons from lesson 4. Ref.watch, where it watches the auth provider and subscribes to auth state. The screen rebuilds to show a spinner when loading, the form when idle or error. Then we have ref.listen, which passes the auth provider and handles navigation and snack bars as side effects. When the state transitions to authenticated, we call context.go products, which navigates the user to product screen without rebuilding. When it transitions to error, we show a snack bar, and inside the login buttons on pressed, we use ref.read, where we pass in the auth provider, and we call the login method, passing in the email and the password, which triggers the entire login sequence. So 3 ref calls, the 3 patterns from lesson 4 applied to a real screen. Now this table shows exactly how each auth state maps to what the user sees and what happens in code. Initial and error both show the login form with the button enabled. The difference is that error also triggers a snack bar through ref.listen. Loading shows a spinner and the button is disabled to prevent double submission. Authenticated triggers navigation through ref.listen and shows a blank screen momentarily while the navigation completes. Notice the clean separation. Ref.watch drives what's displayed, ref.listen drives side effects, and these are two completely independent mechanisms working in parallel. Now, Go router's redirect mechanism is how we protect routes. So every time a navigation is attempted, Go router calls our redirect function before allowing it to proceed. Inside redirect, we read the current auth provider state. If it's authenticated, we return null, meaning allow the navigation. If it's not authenticated and the user is trying to reach the product screen, we return login screen. Go router sends them there instead by default. So the initial state needs special handling. When the app first launches and build method is still checking the token, we don't want to flash the login screen unnecessarily. We also need to connect Go router's refresh listenable to auth provider so the router reevaluates the redirect when auth state changes. This is what makes navigation happen automatically after login. You can have a look at Go router and learn more about it. So once a user is logged in, every API call to Serverpod needs the JWT token in the authorization header. So we solve this elegantly with a second provider, the authenticated DIO provider, that watches both DIO provider and auth provider. Inside, it creates a DIO instance and injects the token from the current auth state as the authorization bearer header. Because it watches auth provider with ref.watch, it automatically updates whenever auth state changes. When the user logs in, all providers watching authenticated DIO provider get a fresh DIO with the correct token. When the user logs out, the token is cleared. So in lesson 6 and beyond, products provider and order provider will watch authenticated DIO provider instead of the plain DIO provider. Logout is 3 steps. First, delete the token from shared preferences. If we didn't do this, a future app launch would find the old token and try to restore the session. Second, set state to auth state.initial. Auth provider is now unauthenticated. And third, call ref.invalidate on products provider and any other provider that holds user-specific data. This ensures a fresh fetch happens if a different user logs in. Once state changes to initial, Go routers refresh listenable files. The redirect function reads the new auth state, finds it's unauthenticated, and returns the login screen. The user is taken there automatically. There's no navigation code in the logout method itself. It's clean and decoupled. So here's a complete picture of lesson 5's auth system. 4 layers working together. The user interacts with the UI layer, login screen, navigation, profile screen. The UI talks to Riverpod through ref. Auth provider holds the state. Auth notifier drives all transitions. Authenticated DIO provider supplies the authenticated HTTP client. The storage and network layer serves the notifier. Shared preferences for the token, DIO for the Serverpod calls or your preferred backend calls. 3 complete flows: login, session restore and startup, and logout, all clean and separated by concern. Now this is a full auth foundation that every lesson from 6 onwards will build from. Lesson 5 is our largest so far and now complete. We built a full production quality authentication system. The user model passes from Serverpod's JSON. All state is a sealed class with 4 compile safe variants. You now have an understanding of what a sealed class is. Auth notifier drives all transitions, startup token check, login with DIO, logout with cleanup. Then the token persistence with shared preferences makes returning users skip the login screen. Then we have the login screen that uses all 3 ref patterns from lesson 4 applied to a real feature. Then we have the go router redirect that protects every route and authenticated DIO provider that supplies an authenticated DIO client to every provider that needs it in the future lessons. The auth foundation is complete. Every feature from here builds on top of it. In lesson 6, we build a product catalog. The first screen a user sees after logging in. We'll use a sync notifier provider to fetch the list from Serverpod's get products endpoint using our new authenticated DIO provider that we just created in this lesson. We'll display it with the async value.when method pattern, spinner while loading, retry button on error, grid when data arrives. We'll add pull to refresh with ref.invalidate, remember in lesson 4, and we'll build the product card widget that shows the product image, name, and price. See you in lesson 6. Welcome to lesson 6. Authentication is done and users can now log in, and we have a JWT token. Now we put that token to work. This lesson is about fetching data from Serverpod, which is our backend in this lesson. You can replace that with whichever backend you're using, mainly the product catalog. We'll build the product model, write a products notifier using the async notifier provider, call the get request with our authenticated DIO client that we created in the previous lesson, and display the results with a sync value. And we'll also add pull to refresh, a retry button for errors, and the product card widget. So by the end of this lesson, ShopWave has a working product screen. There are 6 pieces this lesson has, all smaller than lesson 5. The product model comes first. It's the simplest thing we write today. Then products notifier, which is a fast, real async notifier provider in our code base. Then product screen, which puts a sync value into practice with a real loading, error, and data UI. Then the product card widget, which will be a reusable component, and pull to refresh with ref.invalidate. And finally, wiring the router to show the real screen instead of the placeholder. So these 6 pieces connect directly into the authentication foundation from lesson 5. So we have 4 new files and 1 update. The most important thing to notice is that the products provider.dat will use authenticated DIO provider from lesson 5. The DIO instance that already has a JWT token injected into its authorization header. We don't need to think about auth again. It's already handled. So this is a payoff of building authentication fast. Every subsequent feature gets authenticated API calls for free. So let's create all 4 files empty before starting, then fill them in the order shown in this lesson. Now the product model is the simplest file in this lesson. It's a plain Dart class with 6 fields that map directly to what Serverpod sends in the get product request. So the ID field is a unique identifier we'll use when navigating to the details screen in lesson 7. Then we have the name and image URL, which are what the card shows. Then the price is a double. We'll format it as currency in the product card widget. Description and category are fetched now but used more heavily in lesson 7. From JSON passes the response, and that's the entire file. No logic, no state, just a clean data class. Products notifier extends as sync notifier. The key difference from the synchronous notifier we wrote for auth is that the build method is now async. It returns a future. Riverpod intercepts this. The moment build method starts running, Riverpod sets the state to async loading, and when build method returns a list, Riverpod sets state to async data, wrapping that list. If build method throws an exception, Riverpod sets state to async error. So you write the fetch logic, Riverpod writes the loading and the error states automatically. The build method is elegantly short, 4 logical steps. So you get the authenticated DIO using the ref.watch, passing in the authenticated DIO provider. The token is already in the header. We don't touch auth at all. Then we call DIO.get method on the product's endpoint. Pass the JSON list into a list object using product.fromJSON method, then return the list. That's it. No try and catch required. Now, the product screen is a consumer widget with one job. It calls ref.watch, passing in the product's provider, and then displays the right UI for each async value state. The loading state shows a centered spinner. The error state shows the error message and a retry button. The button calls ref.invalidate, passing in the product's provider, which destroys the failed state and triggers a fresh fetch. That's the role of the ref.invalidate. The data state renders a grid view of product cards, one per product. All three are wrapped in a refresh indicator, so pull to refresh always works. Now pull to refresh is 2 lines of code. When the user pulls down, then Flutter calls our onRefresh async callback. So the first line is ref.invalidate, passing in the product's provider. This destroys the current product state and triggers build method to run again immediately. The UI sees the state change and shows the loading state. Then line 2 is await ref.read, passing in the product's provider.future. This awaits the completion of the running fetch. And why? Because refresh indicator shows its spinner until the callback's future resolves. So without the await, the spinner will dismiss immediately while data is still loading. Now the product card is a pure stateless widget. It receives a product object and an onAdd to cart callback. No Riverpod inside the card itself. So data flows down from product screen, which passes each product to its card. The card has 5 visual elements: the product image loaded asynchronously with cached network image, which handles loading placeholders and error images gracefully, a category badge using a styled chip, the product name with a 2-line marks, the price formatted as a currency string, and the add to cart button, which calls the onAdd to cart callback. There's a utility method worth knowing, the async_value.guard method. In an async notifiers action methods, you sometimes need to set state manually, set loading, make the async call, or set data or error. So the guard method shorthand eliminates the try and catch. So you write state is equals to await async value dot, call the guard method and pass in your function or your logic. For example, dio.post and specify your request. And it returns an async data on success or async error on throw. It's identical to the verbose version. So in build method, you don't need this because async notifier handles the loading, error, wrapping automatically. But in action methods like a refresh method or place order method inside a notifier, guard method keeps things compact. Now the diagram shows where products provider sits in the full dependency tree. At the top, product screen watches products provider watches authenticated DIO provider, which itself watches auth provider to keep the token current. If the user's session changes, authenticated DIO provider updates, and products provider automatically refreshes with the correct credentials. So notice the product card is a plain stateless widget. It doesn't touch Riverpod at all. Data flows down from product screen. So the provider chain from lesson 5 keeps paying dividends. Adding products required 0 auth code because the foundation already handles it. Now the products provider has no autoDispose modifier, and that's intentional. Data is fetched once when the screen first appears and then cached in memory for the entire app session. So when the user navigates to a product details screen and comes back, the products are shown instantly. No spinner, no refetch. The data only refreshes when explicitly asked to, for example, pull to refresh or the retry button. So this is the right behavior for product catalog. Compare this to product detail provided in the lesson 7, which will use autoDispose because product detail data is screen specific and should be freed when you navigate away. So a quick UX enhancement worth knowing, shimmer loading states. Instead of a spinner in the center of an empty screen, shimmer shows ghost cards in the exact shape of the content that's about to appear. So users understand immediately that a grid of products is loading, which reduces the uncertainty that makes loading feel slow. The shimmer package makes this straightforward. You build a product card skeleton that mirrors the card layout with gray placeholder boxes, then wrap it in shimmer.fromColors method and show a grid of 6 skeletons in the loading state. The core lesson code uses a simple circular progress indicator. Now the router update is the smallest change in this lesson, one import and one builder change. So we have to replace the placeholder scaffold with const product screen method. The entire auth redirect stays exactly as written in lesson 5. What this enables is a complete end-to-end flow. User logs in, auth provider transitions to authenticated, go router redirects sends to the product screen. Then the product screen renders and calls the ref.watch, passing in the products provider, and then the build method calls Serverpod with a token. Then the products appear in the grid. So that's the flow. So 4 things can go wrong when fetching products: no network connection, where there's a DIO exception with a connection error, or an unexpired token where Serverpod returns 401, or a server problem, for example, with the error 500, or a request timeout. So in all 4 cases, the exception propagates out of the build method without being caught. Riverpod intercepts it and wraps it in a sync error, and the when method error handler receives it and shows the error message with a retry button. So one error pattern handles every failure mode. The one edge case worth handling explicitly is a 401. An expired token on the product's fetch means the user session has silently expired, so we need to be able to provide good fallback on that. So in that case, calling authProvider.logout method sends the user back to the login screen cleanly rather than showing a confusing failed to load products message. So here's a complete picture, 4 layers. The user navigates, pulls to refresh, taps retry, or taps a card. So the UI layer has product screen refresh indicator, product card, and a sync value.when method, which handles everything the user sees. The Riverpod layer has the product provider watching authenticated DIO provider watching the auth provider, which drives all state. Then Serverpod sits at the bottom or whichever backend you're using, receiving authenticated request and returning product JSON object. So 3 complete flows: fast load, refresh, and error with retry. So notice how little code coordinates all of this. The provider dependency graph does the heavy lifting automatically. Great, so lesson 6 is complete. We built the full product catalog feature on top of the automation foundation from lesson 5. The product model passes from Serverpod's JSON. Products notify uses a sync notifier provider. The build method fetches. Riverpod handles all 3 async states automatically. Product screen uses a sync value for loading, error, and data UIs. Pull to refresh and retry both use ref.invalidate. The product card is a clean stateless widget receiving data from above. The router is wired to the real screen. And throughout all of it, 0 auth code written because authenticated DIO provider handles the token silently. So that is the payoff of building foundations fast. Lesson 6 is done. In lesson 7, we build the product detail screen, and it's where the family modifier gets its fast real workout using the product detail provider that uses the async notifier provider to access the family provider modifier. So it takes in an integer product ID as its parameter. So for example, ref.watch passing in the product detail provider, passing in the parameter maybe ID 42. This gives you a completely independent provider instance for product 40 or product of ID 42. If you pass in an ID like 1, it should provide you an instance of product of ID 1. So that's where family modifiers come into place. So we navigate away and autoDispose cleans it up. Then we get to navigate to another product of ID, maybe 7, and a refresh independent instance is created for that ID. So that's the work of the family provider. The detail screen shows a full production description, a larger image, and the category. So see you in lesson 7. Welcome to lesson 7. So in lesson 6, we built a product list. One provider, one fetch, one list. But clicking on a product needs something different. A provider that fetches a specific product by ID. You can't write a separate provider for every product. That's where the family modifier comes in. One provider declaration that creates independent parameterized instances for each ID. Add autoDispose and each instance cleans up when you navigate away. So this lesson is a family modifier in its natural habitat. Before family, the only way to have parameterized providers was to create a separate top-level provider for every possible parameter value, which is obviously absurd for a product catalog with hundreds of items, right? So the family modifier solves this cleanly. You declare the provider once, annotate it with .family, and specify the parameter type, and then create instances dynamically by passing the parameter when you watch it. So each unique parameter value gets its own completely independent provider instance, its own fetch, its own cache, its own lifecycle. One declaration and limited instances. Lesson 7 is the smallest lesson in the series, just 2 new files and 2 small updates. So the 2 new files are the star of this lesson. The product underscore detail underscore provider, which uses the full async notifier provider.autodispose.family combination, then the product detail screen, which consumes it. Okay, so the router gets one new route with a path parameter, and product card gets its on tap navigation activated. It was a placeholder in lesson 6. Now it navigates to the real detail screen. So small footprint, powerful concept. The family modifier turns a provider into a factory. When you write ref.watch method, passing the product detail provider, passing in the parameter like ID 42, Riverpod checks if an instance for ID 42 already exists. If it does, it returns that cached instance immediately, no network call. If it doesn't, it creates a new instance, runs build method with the argument 42 available as a property, then fetches from Serverpod or your backend and caches the result. Navigate to product 7 or a product of ID 7, and an independent instance for ID 7 is created and managed separately. And then if you decide to navigate back to product 42, the cached result is returned instantly. So each unique argument is its own universe. The parameter must support equality. Primitives like int and string are perfect choices. The combination of autoDispose and family is the idiomatic pattern for detail screens in Riverpod. Family creates an independent instance for each product ID, so navigating to product 42 doesn't interfere with product 7. AutoDispose ensures that when the last widget watching a given instance navigates away, Riverpod destroys that instance and frees its memory. You don't carry around the full detail state of every product the user has ever visited. So you fetch when needed and then you free when done. If the user navigates back to the same product, a fresh instance is created and a fresh fetch runs, which is correct for detailed data that might have changed. Now let's trace the product ID through the system. One integer making 4 hops. Hop 1. The user taps a product card which calls context.push, passing in the product's root path and passing in the path parameter as 42. GoRouter extracts the 42 as the ID path parameter. Then hop 2, GoRouter passes state.path parameter ID to the product detail screen constructor as product ID, which calls int.pass method to convert the string to an integer. Then hop 3, inside product detail screens.build method, ref.watch, passing in the product detail provider, passing in the product ID, creates or retrieves the provider instance for ID is equals to 42. Then hop 4, inside that instance build method, the argument equals 42, the URL becomes products/42. So dio.get method fires and the Serverpod returns the product JSON. Product detail screen is a consumer widget that takes a product ID in its constructor. So inside build method, it passes that ID directly to the family provider. So you call ref.watch, passing in the product detail provider, passing in the product ID. The async value.when method pattern is identical to the products list. Loading shows a spinner, error shows a retry button, and data renders the full product detail UI. The detail layout is a scrollable column, a large hero image at the top, category badge, product name, price in amber, description text, and the add to cart button pinned at the bottom. The add to cart button is currently a placeholder, so we wire it to the cart. provider in lesson 8. The timeline shows the lifecycle of family provider instances. So the user taps product 42, provider 42 is created and build method starts fetching. So the user is on that screen and the instance is alive. They navigate back. The last widget watching provider of product ID 42 is gone. AutoDispose fires and the instance is destroyed. Then the memory is freed. Then they tap on product of ID 7. Then it calls the provider, passing in the path parameters, the product ID as 7, which is a completely separate instance, right? Then it creates a freshly and fetches independently. Then they navigate back. Then the provider with the ID 7 is disposed. At no point do both instances exist simultaneously in memory during normal browsing, and they never share state. So this is the right default for detail screens. The root update in router.dat is minimal but precise. So add the path /products / passing in the path parameter as ID. The column prefix tells go router that ID is a dynamic path parameter. In the builder, extract the parameter with state.path parameters, passing in the key ID, which gives you a string. Pass it to int with int.pass method, then pass that integer to product detail screen via its constructor. The screen stores it and passes it to the ref.watch method in the build method, and that's the full chain. Product card on tap now calls context.push, passing in the path, and this is the activation of the placeholder navigation we left. In lesson 6. A natural question will be, does the family provider cache results between visits? So with autoDispose, our default answer is no. Navigating away disposes the instance. Returning to the same product triggers a fresh fetch. So this is the right default for ShopWave. Product prices and availability can change, and we want the user to always see current data. So there's an option to preserve data, calling ref.keepAlive inside build method, which prevents disposal even with autoDispose. The instance and its data survive navigation, and the user sees instant data if they return. This is appropriate for expensive fetches or slow changing data. For ShopWave, we keep it simple and always refetch. So here's an elegant UX improvement, optimistic prepopulation. The product list we fetched in lesson 6 already has the basic data, name, price, category, image, URL. When the user taps a product card, instead of showing a blank loading screen on the detail screen, we can immediately read that product from products provider and show the basic info while the full detail fetch completes in the background. The user sees content instantly, name and price appear the moment they tap. The description loads when the get a request call returns. So the transition feels instant. Your script shows how to implement this at a direct enhancement to product detail screen. The product card update is a single line. In lesson 6, we left the gesture detector dot on top as a comment placeholder. Now we replace it with context.push, passing in the path. That's it. This one line activates the entire chain we've built. GoRouter extracts the ID, passes it to product detail screen, which passes it to product detail provider via the family modifier, which fetches from the Serverpod or your backend and renders the details. So 6 lessons and 2 files of infrastructure made this one line possible. And this is what paying off technical debt in the right order feels like. Now the family pattern generalizes far beyond product detail. Anytime you need a provider that takes an argument and returns data specific to that argument, family is the right tool. For example, category filtered product list, where each category has its own cached fetch, user profiles, where each user ID gets an independent instance, order detail, where each order ID fetches independently. So the pattern is always the same: one declaration, parameterized instances, and each independent. So the choice of whether to use autoDispose alongside family depends on whether you want data to persist between visits. Detail screens almost always benefit from autoDispose, while category filters might benefit from keeping data alive. So here's a complete end-to-end flow for lesson 7. The user taps a product card. Context.push navigates to /products/42. GoRouter extracts the ID, passes it, constructs product detail screen, passing in the product ID as 42. The screen's build method calls ref.watch, passing in the product detail provider of 42. Riverpod creates a family instance, runs build method, which starts with async loading. Then we get the results from Serverpod itself with a auth token. The JSON comes back, product.fromJSON method passes it, state becomes async data, and the detail screen renders. The user navigates back, autoDispose fires, and the instance is cleanly destroyed. 3 user actions, 1 coherent system. Lesson 7 is complete and it was compact. The family modifier solves the parameterized provider problem cleanly. 1 declaration, unlimited independently managed instances per argument. Combined with autoDispose, each instance lives only as long as the detail screen is visible. AutoDispose async notifies the base class when both modifiers are combined. The arg property gives you the parameter inside the build method. Product detail screen takes the product ID in its constructor and passes it directly to the family provider. GoRouter handles the path parameter and does the int.pass. Product cards navigation is now live. The shopping app is taking shape. In lesson 8, we build the shopping cart, the most interactive feature in ShopWave. Cart notifies a notifier provider with 4 methods. Add item method that handles the case where the product is already in the cart by incrementing quantity. Remove item method deletes the product ID. Update quantity changes the count. And clear method empties everything for post checkout. We'll derive a cart count provider using a select method transformation to drive a badge on the app bar, and we'll build cart screen with a list view of items, quantity controls, subtotals per item, and a grand total. Welcome to lesson 8, the cart. This is notifier provider doing its most natural work, a list of items that changes constantly in response to user actions. We'll build cart item, cart notifier with 4 methods: add item, remove item, update quantity, and clear, using immutable state mutations throughout. We'll derive a cart count provider using the select method for the app bar badge, and we'll build cart screen with quantity controls, line item totals, and the grand total. So by the end, add to cart works on both the list screen and the detail screen. So there are 6 deliverables in this lesson. Cart item is a simple data model, a product plus a quantity. Then cart notifies the core 4 methods, all producing new lists with that spread operator. Then we have the cart count provider that derives a single integer from the cart state for the badge. It uses the select method, so only count changes trigger a rebuild. Then the cart screen is a UI, a list of items with quantity controls and totals. Then we wire up add to cart on both product card and product detail screen. Those placeholder buttons finally do something. And we uncomment the cart invalidation in the logout method so that the cart clears cleanly on sign out. So cart item is a simple 2-field class. The product field carries a full product object, name, image, price, so cart screen can display everything without needing to refetch. The quantity field tracks how many of these products are in the cart. Cart item is immutable. We declare both fields as final and use a const constructor. To update the quantity, we use copywith method, which creates a new cart item with a modified quantity and keeps everything else the same. We also add a subtotal getter, product.price times quantity, which cart screen uses for line item totals and the grand total. Before we write a single method, we need to understand the immutability rule because violating it is the most common bug in notifier provider code. Riverpod detects state changes by comparing the old and the new values with the double equal. When you call state.add method or modify an item in place, the list reference doesn't change. It's the same object in memory. Riverpod compares old state with new state, and if it's true, it doesn't rebuild. Widget appears frozen even though the data changed. So the fix is always to assign a brand new list to state using the spread operator, map method to list method, or where method to list method. So a new list is a new reference, and Riverpod sees the difference and triggers the rebuild. We mentioned this early in lesson 1. Cart notifier has 4 methods. Add item is the most interesting. It checks if the product is already in the cart. If it is, it creates a new list with that item's quantity incremented by 1 using copywith. If it's new, it spreads the existing list and appends a new cart item with quantity 1. Remove item is 1 line. Assign state to a where filtered list, excluding the matching product ID. Then update quantity handles the plus and minus buttons in cart screen. If the new quantity is 0 or less, it removes the item entirely. Otherwise, it maps over the list and applies copywith to the matching item. Then clear is 1 line where we call the state is equals to passing in an empty list. It's used on logout and after checkout. The add item method has a decision branch. So first we check if the product is already in the cart by searching for an item with the same product.id. If found, we create a new list by mapping over the existing state. For the matching item, we call copyWith to produce a new cart item with quantity incremented by 1. For all other items, we return them unchanged. If not found, we spread the existing state into a new list and append a fresh cart item with quantity 1. Both branches assign a brand new list to state. So Riverpod detects the new reference and every widget watching cart provider rebuilds immediately. Cart count provider is a derived provider. It reads cart provider and computes a single integer. the total number of items across all cart entries. The app bar badge only cares about this number. We use the select method to create a fine-grained subscription. The badge widget only rebuilds when the count actually changes, not on every cart mutation. If the user changes an existing item's quantity from 2 to 3, the count goes from 6 to 7. Rebuild happens. If the user swaps one item for another at the same quantity, the count stays the same, so no badge rebuild. This is the select method pattern in its most practical form. Cart screen is a consumer widget that watches cart provider. If the list is empty, it shows a centered empty state, a cart icon, and your cart is empty message with a button to browse products. When items exist, it renders a list view of cart item tile widgets. Each tile shows the product image, name, price, quantity controls, and a delete button. Below the list is a summary section with a grand total computed using fold method over all item subtotals. At the bottom is a checkout button that shows the total and is a placeholder for lesson 10. Ref.read for all the action buttons, and they trigger methods and not subscriptions. The quantity controls need one smart edge case. When a user taps the minus button on an item that already has quantity 1, the new quantity will be 0. Update quantity handles this. If the new quantity is 0 or negative, it calls remove item instead of copy with. the item disappears from the cart cleanly. This means the minus button doubles as a delete mechanism for the last item in the cart. The user doesn't need to find a separate delete button when tapping down from one. We also show an explicit trash icon for cases where the user wants to delete immediately regardless of quantity. So both routes go through cart notifier method, clean and consistent. The grand total is computed with a single fold method call over the cart items. Cart item has a subtotal getter that returns price times quantity, and fold method accumulates this into a running sum. So this runs inside cart screen's build method. It's not a separate provider, so every time the cart changes and the widget rebuilds, the total is automatically recomputed. No stale data possible. You can optionally extract this into a cart total provider using provider, which makes it easier to test in isolation and share the total value across multiple widgets. For ShopWave, inline fold method in the widget is clean enough. Wiring add to cart is reactivation points. In product screen, the on add to cart callback passed to each product card is now ref.read passing in the cart provider.notifier and calling the add item method passing in the product, replacing the lesson 6 snack bar placeholder. In product details screen, the add to cart buttons on press is the same call. The screen is already a consumer widget, so ref is available. After both calls, show a brief snack bar confirming the item was added or the quantity updated. And in the product screen upper, ref.watch passing in the cart count provider drives a badge widget showing the live item count. 5 lessons of infrastructure activate in 3 one-liners. The select method pattern deserves a deeper look. Without it, the upper badge widget watches a full cart provider. Every cart mutation, including quantity changes that don't affect the badge count, will always trigger a badge rebuild. So with cart count provider using the select method, the badge widget only rebuilds when the total item count changes. If the user has 6 items and changes a quantity from 2 to 3, the count goes from 6 to 7. Badge rebuilds. If the user removes one item and adds a different one at the same quantity, the count doesn't change. Badge doesn't rebuild. So for a simple badge, the savings are small, but the intent is clear. The widget cares about the count only, not the full cart. Every cart needs an empty state. Cart screen checks if the items list is empty at the start of build method. If it is, we render a centered empty state with a muted cart icon with a message your cart is empty, and also a browse products button that navigates back to the products root. If items exist, we render the normal list view. This transition happens automatically. When the user removes the last item, the cart becomes empty, the widget rebuilds, and the empty state appears. Same when cart notifier.clear method is called after logout or checkout. So there's no special handling needed here. The immutable state update triggers everything automatically. The last piece is the simplest. In lesson 5, authNotify.logout method, we left a comment. ref.invalidate passing in the cart provider. Now we uncomment it. This lesson destroys a cart provider and replaces it from build method, which returns an empty list. So the critical reason is if user A has 3 items in their cart and logs out, user B who logs in on the same device should start with an empty cart, not user A's leftover items. The invalidation ensures clean separation between sessions, so one uncommented line. That's all. So here's a complete cart system. The user taps add to cart. Product cards callback calls ref.read passing in the cart provider.notifier, calling the add item passing in the product. Cart notifier builds a new list and assigns it to state. Riverpod detects the new reference and rebuilds all watches. Cart screen shows the new item. Cart count provider updates the up bar badge. Then quantity changes go through update quantity, either a copy with method for increment or decrement or a where filter for zero quantity removal. Then logout calls ref.invalidate on cart provider, resetting it to an empty list. So every action is a pure function in producing a new list, no mutation anywhere. Now lesson 8 is complete. ShopWave now has a fully functional shopping cart. Cart item is an immutable model with copy with. Cart notifier has 4 methods: add item checks for duplicates and increments quantity or appends a new item. Remove item filters with where. Update quantity handles the edge case of reaching 0. Clear resets to an empty list. Cart count provider derives the item count using select for fine-grained badge updates. Cart screen renders items with quantity controls and a grand total. So the add to cart buttons are live on both product screens, and logout properly clears the cart. In lesson 9, we do go deep on provider composition, providers watching other providers. We'll explicitly trace the full dependency graph, how the auth token flows from auth provider into authenticated DIO provider, into products provider, and into the orders provider that's coming in lesson 10. We'll build an order summary provider that combines cart state and auth state into a single derived value for the checkout flow. See you in lesson 9. Welcome to lesson 9, provider composition. This is the architecture lesson. We've been composing providers all along without fully naming what we were doing. Now we make it explicit how providers watch other providers, what the complete ShopWave dependency graph looks like, why the auth token flows automatically into every API call, and how to build providers that combine multiple sources of state. This understanding is what separates someone who uses Riverpod from someone who designs with it. Provider composition means that providers can declare their dependencies on other providers by calling ref.watch inside their builder. So this creates a live dependency. When the dependency changes, the dependent provider automatically updates. Without composition, you'd pass DIO as a constructor argument, thread the auth token through method parameters, and manage everything manually. With composition, each provider declares what it needs, and Riverpod wires it all together. Dependencies are injected automatically. Changes propagate through the graph without you writing coordination code. It's dependency injection without a service locator or a container. So here's a complete ShopWave dependency graph. 3 tiers. At the foundation, DIO provider, auth provider, and cat provider. They have no dependencies on other providers. At the second layer, or at the second tier, is the authenticated DIO provider, which watches both DIO provider and auth provider. It creates the DIO instance with the auth token injected. At the third layer, the business logic providers that watch authenticated DIO provider, like the products provider, order provider, product detail provider. Also in the tier 3, the derived providers like order summary provider, which combines cat and auth. And also we have the cat count provider, which derives from cat, as we discussed in the previous lesson. So this is a graph we've been building all along, made explicit. The auth token chain is the most important composition in ShopWave. Auth provider holds the authenticated user, including the JWT token. Authenticated DIO provider watches auth provider with ref.watch. When auth changes, it rebuilds and produces a DIO instance with a new authorization header, or removes the header on logout. Products provider, order provider, and product detail provider all watch authenticated DIO provider. So when the token changes, they all rebuild automatically. Log in once and every API call in the app is authenticated. There's no manual token threading anywhere. So this is composition working at its best. One change propagates through the entire graph without you writing coordination code. The mechanism that makes composition work is ref.watch inside a notifier's build method. When products notifier calls ref.watch passing in the authenticated DIO provider in build method, it creates a dependency link. Riverpod tracks this. Products notifier depends on authenticated DIO provider. So the moment authenticated DIO provider changes, because the user logged in and the token updated, Riverpod knows it needs to rerun products notifier's build method. The build method executes again, calling await dio.get, passing in the respective path with a new authenticated DIO instance. So the product list refetches automatically, and you don't write a single line of coordination code when doing this. Here's a cascade in sequence. So the user logs in, auth provider transitions to authenticated. That's step 1. Riverpod detects that authenticated DIO provider watches auth provider, so it rebuilds authenticated DIO provider with a new token in the header. That's step 2. Riverpod then detects that products provider, order provider, and product detail provider all watch authenticated DIO provider, so it invalidates each of them. Products provider refetches with the authenticated DIO. The others reset and wait for their next use. Step 3. The UI, every widget watching any of this providers rebuild with fresh authenticated data. So 1 login, 3 cascading steps, 0 coordination code you wrote. The authenticated DIO provider implementation is the clearest example of the bridge pattern in Riverpod. It takes 2 dependency, DIO provider for the base HTTP client and auth provider for the current token, and combines them into 1 authenticated DIO instance. Every protected API provider watches this single bridge instead of managing auth themselves. So if the authentication model ever changes, say we switch from JWT to OAuth, we update only this one provider. Products provider, order provider, product detail provider are completely unaware. So this is single responsibility enforced by the dependency graph. Order summary provider is the new code in lesson 9, and it's a perfect demonstration of derived providers. It watches both cat provider and auth provider. From cat, it takes the items list and computes the total. From auth, it takes the user's name to display on the confirmation screen. It packages all of this into a single order summary record. Then the checkout screen watches just this one provider instead of reading cat and auth separately. So when the cat updates, order summary provider recomputes automatically. When the user changes, which shouldn't happen mid-checkout, but if it did, the summary updates. So one data source for the checkout flow, automatically reactive. Now, lesson 9 introduces several derived providers that show different composition patterns. Cat count provider takes a list and derives an integer, the item count for the badge. Cat total provider takes the same list and derives a double, the grand total for the checkout button. Order summary provider combines two different sources, cat and auth, into a single record for the checkout flow. And is checkout ready provider is a Boolean gate, true only when the cat has items and the user is authenticated. So each of this is a plain provider reading other providers. They don't call APIs, they don't modify state, they just derive values reactively. Understanding when reevaluation happens is essential for writing effective or efficient Riverpod code. So a provider reevaluates when any provider it watches changes, when it's explicitly invalidated or refreshed, or when a watch dependency is invalidated and the cascade reaches it. It does not reevaluate when a provider it reads or when a provider that it does not watch changes. So ref.read creates no subscription. It also doesn't reevaluate when an unrelated provider changes anywhere else in the app. And when using select method, it only reevaluates when the selected value actually changes. So even if the underlying provider emits a new value, it does not change. The dependency graph is precise. Only declared dependencies trigger reevaluation. Only declared dependencies. Now, the distinction between ref.watch and ref.read becomes critical in provider composition. In a notifiers build method, we use ref.watch to declare reactive dependencies. When the dependency changes, build method reruns and the full refresh cascade happens. In a notifiers action methods like placeholder, place order method, or add item method, you need to use the ref.read. You want the current value at the moment the action fires. I know we have mentioned this so many times, but the number of times we have repeated this, I'm sure you'll never forget. You don't want place order method to be retriggered every time the auth token refreshes. Actions are point in time operations. Build method is a reactive setup. So this is the same rule from lesson 4, lesson 1, lesson 2. It's applied throughout. So here's the fully annotated ShopWave dependency graph. So let's read it to top to bottom. Infrastructure at the top, we have the DIO provider, auth provider, and the CAP provider. No dependencies, they are the roots. Now the amber arrows show the authentication bridge. Authenticated DIO provider watches both DIO provider and auth provider. The white arrows show business logic providers watching the bridge. That is the products provider, order provider, product detail provider. Now the amber arrows pointing to order summary provider shows it watching both auth and cat directly. And at the derived tier, cat count provider, cat total provider, and is checked out ready provider watch. They watch cat or auth to derive simple values. So this is a full picture of everything built in lessons 2 through 9. There's one critical mistake to avoid in provider compositions, which is circular dependencies. If provider A watches provider B and provider B watches provider A, whether directly or through a chain, you get an infinite rebuild loop. Riverpod catches this and throws a provider exception immediately rather than silently looping, which is helpful for debugging. The guard against circular dependencies is simple. Always think in directed acyclic tiers. Dependencies flow downward. If you find yourself wanting two providers to depend on each other, the solution is to extract the shared state into a third provider that both can watch independently. In the ShopWave graph you saw earlier, notice that arrows never go upwards. They always flow from foundation towards business logics towards derived. Now, lesson 9 is the understanding lesson, and now the picture is complete, right? Provider composition means providers declaring their dependencies with ref.watch inside the build method. The ShopWave graph flows in 3 tiers: infrastructure at the top, the auth bridge in the middle, business logic and derived providers at the leaves. One login event cascades automatically through the entire graph. Order summary provider combines cart and auth for the checkout flow. Is checkout ready provider gets the checkout button. The watch in build rule controls what's reactive. So composition is what makes the code testable, and circular dependencies flow in one direction, always downwards. So with this understanding, building orders in lesson 10 is straightforward. Now in lesson 10 we build orders, the checkout flow completing the core shopping experience. Order notifies an async notify provider with a custom place order method, action method that posts to Serverpod's order endpoint. On success, the cart clears via ref.invalidate method and the order appears in the history. We'll also build an order history screen using a simple async notify provider for get orders. The order summary provider we built in this lesson feeds directly into the checkout UI. So see you in lesson 10. Welcome to lesson 10, orders. This is a lesson where the shopping loop closes. A user has browsed products, added items to the cart, and is ready to check out. Place order method calls Serverpod's post orders endpoint with the cart contents. On created, the cart clears automatically and the order appears in the history. So every feature from lessons 5 through 9 feeds into this moment. We also build the order history screen with a get, where we get the orders using the async notifier provider for read-only data one more time. Now there are 6 deliverables to close the core shopping loop. The order model is our last data class, straightforward, similar to product. Order notifier combines 2 responsibilities: its build method that fetches order history and its place order action method that posts the new order. Checkout screen is the UI entry point. It reads the order summary from lesson 9 and calls place order method. The success screen confirms the order with the ID from Serverpod's response. The order history screen reuses the async value pattern we know from products. And the router, it gets the final routes to complete the navigation. So the order model is our last data class. 5 fields map directly to Serverpod's get orders response. The ID is assigned by Serverpod at creation and is what we show on the confirmation screen. The status field uses an order status enum pending through delivered, which with each value mapping to a color chip in the history screen. So the items list contains order item objects that capture the product ID, quantity, and the price at this time of purchase. This is important because product prices can change, but the order total must be fixed. Created art is passed from ISO 8601 string and formatted for display. Order notifier has two distinct responsibilities on the same async notifier. The build method handles reading. It fetches the order history from the get orders endpoint and returns it as a list. This runs once when the provider is first watched, exactly like products notifier. Then the place order method handles writing. It's a custom action method that takes the order summary from lesson 9 and posts it to Serverpod. On success, it invalidates the cart, prepends the new order to the list, and returns the confirmed order so the checkout screen can navigate to the confirmation screen. On failure, it transitions to the async error so the UI can display the problem. Read and write cleanly separated with one notifier. The place order method follows a precise 6-step sequence. So the very first line sets state to async loading. The place order button shows a spinner immediately. Then the post orders hits Serverpod with the cut items and total amount from the order summary. On created, we pass the new order object from the response. Then ref.invalidate, passing in the cart provider. This is the moment the cart empties. We prepend the new order to the existing state list, so history is immediately visible. Finally, the state update triggers ref.listen in checkout screen, which pushes to the success screen with the order ID. On any error, we set async error. Ref.listen shows a snack bar and the cart is deliberately not cleared so the user can retry without losing their items. place order method is where async value.card earns its place in our code base. In build method, async notifier handles loading and error wrapping automatically. We never call guard method there. But place order is an action method that manually sets state to async loading before the async call. After that, we need to wrap the result in async data on success or async error on failure. The verbose way is a try and catch block that sets state in both branches. Guard is a shortcut. It runs the future and returns async data if it resolves or async error if it throws. So 1 line instead of 5. After the response, 2 things happen in parallel. First, ref.invalidate passing in the cart provider. This destroys the cart, which rebuilds to an empty list. The badge drops to 0. Then the cart screen's empty state appears and the order summary provider recomputes to an empty order summary. Second, we prepend the new order to the current order state list, so the history screen immediately shows a new entry without a separate network call. Both happen before ref.listen fires the navigation. By the time the success screen appears, the cart is already empty and the order is already in history. The user experience is quite seamless. The entire app reflects the order placement atomically. Now the checkout screen is a consumer widget with 3 data sources. Ref.watch, passing in the order summary provider, provides the display data, username, items list, and total, all from lessons 9's composition work. Ref.listen on order provider fires when the order state changes. It navigates to the success screen on async data and shows a snack bar on async error. Ref.watch, passing in the is checkout ready provider, controls the button's enabled state. The place order button shows 3 visual states: idle with a total displayed, loading with a spinner that's also disabled to prevent double submission, and after an error the button re-enables so the user can retry. The cart is not cleared on error. The user keeps their items. Order success screen is a simple stateless widget that receives the order ID as a constructor argument from Go router's path parameter. It shows a large green checkmark with a pulse animation. The order ID, a reassurance message that a shipping notification will be sent, and 2 navigation options. View order history pushes to the order's endpoint, so the order's path or route, so the user can see the new order immediately. Continue shopping using context.go, not push, which replaces the entire navigation stack. So the user can't back navigate into the checkout flow after placing an order, which is the correct UX, right? The order is already placed and the cart is already empty. Now the order history screen is structurally a copy of the product screen, the same consumer widget, pattern watching, and a sync notifier provider with a sync value. Loading shows a spinner, error shows a retry button, data shows a list view of order list tiles. Each tile has the order ID, a color-coded status chip, green for delivered, amber for processing, blue for shipped, the item count, the formatted date, and the total in amber. So the list is sorted newest first because place order prepends. When the user navigates from the success screen to history, the new order is already at the top of the list. The prepend happened before navigation. Now the order status enum has 5 values, each mapping to a distinct color code in the order history tiles. Pending uses a neutral gray, the order is received but not yet acted on. Processing uses amber, work is underway. Shipped uses blue, it's on its way. Delivered uses green, success. Cancelled uses coral, something went wrong. So a single switch expression on the enum produces the chip color, border color, and label text. This function is called in every order list tile, so the mapping is defined once. Status changes are fetched fresh when the user pulls to refresh. Same ref.invalidate pattern as the product screen. Now here's a complete shopping loop. Browse, product screen and product detail screen, powered by products provider and products detail provider. Then cart, which is a cart screen with add, remove quantity controls, powered by cart provider. Then checkout, which uses the checkout screen, reading order summary provider and calling place order action method. Then confirmed, which calls the order success screen with the order ID and the cleared cart. Then we have the history, which calls the order history screen, showing all past orders via order provider. And then the loop continues. Continue shopping navigates back to browse. So 10 lessons of building converge on this single user journey. Now the router gets 3 new routes and 1 activation. So we have the checkout that maps to checkout screen and is already protected by the auth redirect we wrote in lesson 5. Unauthenticated users are sent to log in automatically. Then there's the order success, passing in the path parameter, which extracts the order ID as a path parameter and passes it to order success screen. Then we have the orders route, which maps to the order history screen, also auth protected. And then there's a cart screen's checkout button placeholder, which showed a snack bar since lesson 8, is now activated, calling the context.push, specifying the route. So the router is actually complete. Every screen in ShopWave is now reachable. Here's a complete provider architecture of ShopWave after lesson 10. 11 providers across 3 tiers: infrastructure tier, DIO provider, auth provider, cart provider, all with no dependencies on other providers. Then the auth bridge, authenticated DIO provider combining DIO and auth. The business logic tier, products provider, order summary provider, product detail provider, and the derived cart count, cart total, and is checkout ready providers, which we are calling the derived providers. Every provider we wrote in every lesson is on this graph. We built this incrementally, 1 provider per feature, and it composes it to a complete working architecture. Now lesson 10 is complete and the core shopping loop is closed. We have a production quality order model with price snapshots. Order notifier combines read and write responsibilities cleanly. Async value.card method handles the post result without boilerplate. Cart invalidation and history prepending happen atomically after the items are created. Checkout screen reads the order summary from lesson 9 and drives navigation via ref.listen. The success screen clears the navigation stack so users can't back into checkout. The history screen reuses the async value.when method pattern from products. The router is complete. Browse, cart, checkout, confirm, history. The loop works end to end. In lesson 11, we shift from feature building to robustness. DIO exception interceptors that catch errors globally before they reach individual providers. Retry logic, both automatic on transient failures and manual with ref.invalidate. Global error snack bars via a top-level ref.listen in the app root. So optimistic UI updates for actions like adding to cart, show the change immediately, and revert if the server rejects it. So there's a few error handling mechanisms that we're adding. See you in lesson 11. Welcome to lesson 11. The app works. We proved that across 10 lessons. Now it needs to be robust. Robust means when things go wrong, and they will, the user sees a human message, not a stack trace. It means loading states that look like the real content, not a spinner in the void. It means actions that feel instant even before the server confirms. So the lesson is the difference between an app that works and an app that feels professional. So no new providers, just purely enhancing what's already built. So we have 6 targeted improvements. The first 2 work together. A DIO error interceptor catches raw exceptions and converts them into structured app error objects with human messages. Third, a global error listener in the app root that surfaces any provider error as a snack bar without duplicating the listener in every screen. Fourth, shimmer skeletons replacing the bland spinner in the product's grid. Fifth is the optimistic UI for add to cart. The cart updates instantly because it's local state, no server round trip needed. Then sixth is the automatic logout on 401. When the auth token expires, the interceptor handles it transparently. The DIO error interceptor is the most impactful single addition in this lesson. It's added to the interceptors list in DIO provider, which means every single network call in ShopWave passes through it. When any request fails, a socket exception for no internet, a 4141 expired token, or a 500 from the server, the interceptor catches a raw DIO error, classifies it, and rethrows a clean up error object with a user message string containing something a human can actually read. Providers don't change, they still catch errors, but now the error they catch is a structured app error with a ready to display message. The when method error handler just calls error.userMessage instead of error.toString. App error is a sealed class with 4 variants, each carrying a user message string. Network error covers connection failures, no internet, timeout, connection refused. Auth error covers 401 responses, either session expired, token invalid. Server error covers 500 level responses. Validation error covers 422 and bad request responses. Every variant has a user message field, so any error handler in any screen can call error.userMessage and get a string that's safe to show the user. The sealed class also enables switching on the variant. A 41 should call authProvider.logout method. A network error should show a retry option, and a validation error might need to highlight specific form fields. The global error snack bar is a safety net. Instead of adding a ref.listen for every handling to every single screen, we add one ref.listen in ShopWave app, the root widget. ShopWave app becomes a consumer widget and listens to key providers. The condition is precise, only show a snack bar when the previous state did not have an error, but the next state does. This prevents the snack bar from flashing every time the widget rebuilds. The snack bar shows error.user message from a structured app error, a human-readable string. Screens that need specific error handling like checkout screen navigating away on success still add their own local listeners. So the global listener is a catch, all for anything that slips through. The 401 autologout is perhaps the most elegant part of the interceptor. Without it, when a user's token expires mid-session, every API call returns 401 unauthorized and every screen shows failed to load with no explanations. The user is confused and stuck, so with the interceptor, the moment any request returns 401, the interceptor detects it and calls the auth_provider.logout method, which clears the token, resets auth state to initial, and clears the cat. Go routers redirect fires and the user finds themselves at the login screen with a snack bar that says your session expired, please log in again. Clean, transparent, and recoverable. Shimmer skeletons are one of the highest impact UX improvements in mobile apps. A spinner says something is loading but gives the user no information about what or how much. A shimmer skeleton says here is the shape of the content coming. The user can already mentally orient to the layout. So research consistently shows shimmer skeletons reduce perceived load time by 20 to 40%, even when the actual fetch time is identical. We've seen this even when loading a big app like YouTube. The implementation uses a shimmer package. Product card skeleton mirrors the product card layout with gray boxes. We show 6 of them in a grid view during the loading state. The shimmer.fromColors wrapper adds the sweeping highlight animation using warm cream tones that match the app palette. Now the skeleton design principle is precision mirroring. Every element in the skeleton matches its real counterpart. The image placeholder is the same height as the cached network image. The category badge placeholder is the same width and height as a real chip. The name takes 2 lines of the same height. The price placeholder is the same horizontal space. The button placeholder is the same height and weight. When the real content arrives, the transition looks like a color swap, not a layout shift. Layout shifts are jarring. The goal is for the user to barely notice the transition from skeleton to real content. Optimistic UI means updating the interface immediately before the server confirms. For ShopWave's cart, we already have this without thinking about it because cart provider is local notifier provider state, not an API call. Tapping add to cart calls add item, which synchronously updates a dart list in the same frame, right? The badge updates in the same frame, no network, no wait, no spinner. This is the natural advantage of keeping non-persistent UI state in local Riverpod state. For actions that do require server round trip, say favoriting a provider, the optimistic pattern is update state immediately, fire the request asynchronously, and revert the state change only if the request fails. Show a snack bar for the failure, and then the user is instant in the happy path and recoverable in the failure path. So there are 2 retry strategies for 2 different situations. Manual retry is a ref.invalidate pattern we have used throughout the course. The error screen shows a retry button. The user taps it and ref.invalidate triggers a fresh fetch. This is the right approach for network errors. The user knows they have lost connection, they fix it, they tap retry. Automatic retry with exponential backoff belongs in the DIO interceptor. When a 5-something server error occurs, which may be a transient blip, the interceptor waits 500 milliseconds and tries again, then 1 second, then 2. If all retries fail, it throws an app error. Never apply automatic retry to 400 and something errors. A 400 or 401 will fail on every retry because the problem is deterministic, not transient. Error messages are a user experience, not a debugging tool. So the user who sees socket exception, failed host lookup, api.showwave.com, node name or server name provider or not known, blah blah blah, lands nothing. The user who says no internet connection, please check your network, understands both what happened and what to do about it. Our app error structured class ensures every error category maps to a user appropriate message. Network errors explain the connection problem. Auth errors explain the session and direct to login. Server errors are honest about uncertainty. Validation errors pass through the server specific message since the server knows exactly what validation rule was violated. Empty states are not edge cases. They are guaranteed to appear for every new user. The first time someone opens the cart, it's empty. The first time they view order history, there are no orders. How you handle these states says a great deal about the app's quality. A blank white screen with no content is confusing. The user doesn't know if something failed or if the screen is simply empty. A well-designed empty state has a relevant illustration, a plain language explanation of why it's empty, and an action that takes the user somewhere useful. Every empty state in ShopWave answers two questions: what happened and what should I do next? Not every loading situation calls for the same indicator. So when the product screen loads for the first time, the shimmer skeleton grid is correct. It shows the shape of the content arriving. When the user taps place order or login, a spinner inside the button is correct. Localized loading that keeps the button in place and prevents double tapping. When the user pulls down to refresh, the platform's native refresh indicator is correct. It's a standard gesture with expected feedback. When Go router navigates between screens, no loading indicator is needed. The slide animation is a transition. Matching the indicator to the situation signals that the app understands its own interaction. Overusing spinners signals the opposite. Now, robust error handling has multiple layers. So we have layer 1, the DIO interceptor. This is the outermost layer. It catches raw exceptions before they reach providers, classifies them, and rethrows structured app errors. Layer 2, Riverpod's async value mechanism, which wraps any unhandled throw into async error automatically, preserving the error and stack trace for the UI layer. Layer 3 is the .when method error handler in each screen that renders the error in line with a retry option. Then layer 4, the global root listener, which is the safest net that catches any error without a specific screen handler and shows a brief snack bar. So most errors are caught at layer 1 or 3. Layers 2 and 4 ensue nothing is ever silently swallowed. Now lesson 11 is complete. We upgraded ShopWave from an app that works to an app that's robust. The DIO, error interceptor, and app error sealed class from a consistent error classification layer. The global error listener in the app root is a safety net for anything unhandled. Shimmer skeletons replace spinners in the products grid. The cart was already optimistic because it's local state. For one, responses trigger automatic logout and redirect. Retry strategies match the error type. Error messages speak to user in human language, and the empty states are intentional and actionable, and loading indicators match their context. So one lesson away from complete. One more to go. Lesson 12, the graduation lesson. So we'll review the full ShopWave code base and evaluate the architecture, what worked well, what the constraints are, and what would change for a team of 10 rather than a team of 1. We'll write proper unit tests for cart notify and order notify using ProviderContainer with mocks, putting into practice what we covered in lesson 9's testability section. And we look at what changes at scale, Riverpod generator for annotation-based providers, larger team conventions, performance profiling. So see you in lesson 12. The final lesson of the ShopWave series. 11 lessons of building are behind us. Today we step back from writing code and look at what we built. a complete architecture review, honest reflection on what worked and what we'd do differently, proper unit tests using ProviderContainer, a preview of what Riverpod generator changes, and a lot of what comes after this series. So this is the lesson where the pieces click into a complete picture. So let's start with the numbers. 12 lessons, 11 providers across the 3 dependency tiers, 6 fully implemented screens with real navigation, 4 distinct provider types: plain provider, notifier provider, sync notifier provider, and the family modifier, 1 complete e-commerce loop from browsing to confirmed order, and 0 service locators. All dependency injection is handled by the Riverpod provider graph itself. We built something real incrementally, lesson by lesson. Now let's review what we got right, what has cost, and what we'd change. 6 things that worked particularly well. The feature first folder structure meant every lesson added 1 folder. The existing code was never scattered. The authenticated DIO provider bridge was the most impactful single decision. 11 lessons of protected API calls written without once thinking about auth token injection. The sealed auth state eliminated null bugs by construction. CAT immutability made CAT notifiers logic simple and reliable. Order summary provider is a textbook composition. Checkout screen reads one thing and gets the right answer reactively. And the Go router bridge meant authentication and navigation were generally decoupled. Here the honest assessment of the cost. Manual provider declarations are the biggest economic issue at scale, but Riverpod generator eliminates this. Auth notifier does more than one thing. At team scale, the session restoration logic belongs in its own service. Then order notifier combining history and placement is a pragmatic simplification. It's fine for ShopWave, but you need to split it at scale. Then there's no offline support, which is a deliberate educational simplification. Hive or SQLite will integrate cleanly into the provider graph as another infrastructure tier provider. Then pagination for products is absent. In production, that's a priority. Then CAT doesn't survive restarts. A one method change to catnotify.build fixes this. So none of these are architectural failures. They are known simplifications made for educational clarity. Catnotify is the easiest provider to test because it has no external dependencies, right? Create a provider container with no overrides, read the CAT provider, and call methods directly on the notifier. The tests are pure logic, no network calls, no mocks, no setup beyond creating the container. They run in microseconds, and because we wrote CAT notifiers methods with immutable list replacements, the tests are also straightforward to reason about. Add an item, read the state, assert on the result. The immutability discipline we kept throughout lesson 8 makes the test exactly as clean as the implementation. Product notifier needs 2 overrides: mock DIO returning predefined JSON and fake auth notifier returning an authenticated state. Everything else is a real implementation. Products notifiers build method runs for real. It fetches from the mock DIO, passes a response through product.fromJSON method, and returns a list. The test asserts on real passing behavior against control data. You can also test the error path, configure mock DIO to throw a DIO exception, and verify the provider reaches a sync error state. The composition that makes the app work is the same structure that makes it testable. Every dependency is a SIM you declared explicitly, and every SIM is a point you can override in tests. The test pyramid for ShopWave follows the standard shape. Most tests are unit tests, fast, no network, using ProviderContainer with overrides. CAT notifier needs no overrides at all. Product notifier and order notifier need mock DIO and fake auth notifier. Model serialization tests from JSON to JSON are pure unit tests. Some tests are widget tests using Flutter's test framework with a provider scope override, verifying that screens render correctly in different states. Few tests are end-to-end tests against a real Serverpod test instance. Those are slow and expensive but give the highest confidence in the full user journey. Riverpod generator is the annotation-based approach to writing providers. Instead of manually declaring the provider and the notifier class separately, you add an @Riverpod annotation to the notifier class, run build runner, and the generator produces the provider declaration in a .g.dat file. The runtime behavior is identical, the same provider graph, the same state management, the same dependency injection. The difference is ergonomic, less boilerplate to write and maintain. Learning the manual way fast, which we did across 12 lessons, makes the generated code feel fully legible. So when you use the product notifier in generated code, you now know exactly what it means. 4 ideas that constitute the Riverpod mental model. First, state is a stream, not a variable. A provider doesn't hold a value at a point in time, it holds a stream of values over time. Ref.watch subscribes to that stream. Second, dependencies are declarations. When you write ref.watch passing in the authenticated DIO provider in build method, you're not fetching the value. You're declaring a dependency that the framework uses to build a reactive graph. Third, state transitions are facts. When cat notifier assigns state is equals to new list, it records a new fact. Every subscriber sees it simultaneously. Then fourth, the graph is an architecture. The provider dependency graph is not an implementation detail of the architecture, it's the architecture. It's explicit, visible, and enforced by the compiler. The 6 things that change at team scale. Riverpod generator becomes non-negotiable. The boilerplate of manual declaration multiplies with team size. Feature boundaries become package boundaries with explicit APIs. The repository pattern inserts a testable layer between notifiers and the network, making the data strategy swappable without touching providers. And the data strategy is network fast, cache fast, offline fast. A local persistent layer like Hive or Ether plugs in as another infrastructure provider, invisible to the business logic tier. Then infinite scroll pagination uses a specialized notifier that grows state incrementally. And a shared test doubles layer eliminates copy-pasted mocks. The architecture we build scales into all of this. It doesn't need to be replaced, just grown based on the team size. So here's the one last time, the complete ShopWave dependency graph. 3 infrastructure providers at the root with no dependency of their own. The authentication bridge in the middle tier watching both DIO and auth, producing the authenticated client for every downstream. 6 business and derived providers in the third tier, each with clear single-purpose ownership. 11 providers, 3 tiers, arrows flow in one direction. We built this incrementally, 1 provider per feature lesson, and it combines into a complete coherent architecture. Every arrow is a dependency we declared explicitly. Every dependency is the same we can override in tests. So there are 6 concrete next steps. Write these tests. Start with cat notifier, which needs 0 setup, then progressively add mock DIO for network dependent providers. Switch to Riverpod generator. Migrate 1 provider at a time. The generated code is semantically identical. Add cat persistence. It's 1 change in cat notifier.build method and 1 call in every mutation method. Add product search, a new family provider. 0 changes to existing providers. This is exactly how the architecture should scale. Build your own app. The 3-tier graph and notifier patterns are domain agnostic. Apply them to any problem and read the Riverpod documentation. After 12 lessons, the docs will be fully legible and the advanced topics like keep alive, provider observer, and lifecycle management will make immediate sense. So there are 5 principles worth carrying into every Riverpod project you build after this series. Ref.watch in build, ref.read in methods, the most fundamental distinction. I know I have repeated it so many times. Always produce a new list, never mutate, because Riverpod uses equality comparison and a mutated list is invisible to the framework. Dependencies flow in one direction. Circular dependencies are always a design problem, never Riverpod. It's not a Riverpod limitation. Each provider owns one concern. The authentication concern belongs in authenticated DIO provider, not scattered across 6 notifiers. And errors should be structured. App error is not overhead. It's a difference between an app that works and an app that communicates. So keep these 5 principles and your Riverpod code will be maintainable. So we built ShopWave, a production quality Flutter e-commerce application with authentication, a product catalog with detailed screens, a fully functional cart, a complete checkout and order flow, a 3-tier Riverpod dependency graph, structured error handling, shimmer loading states, and proper test infrastructure. 12 lessons ago, the canvas was blank. Today, it's a working app that demonstrates everything Riverpod is capable of. You understand not just how to use Riverpod, but how to design with it. That's distinction between using a tool and designing with it is a real graduation. So take this forward. So here's a complete lesson catalog, 12 lessons, each with clear deliverables. Please go ahead and you can always review back. They'll always be here. So 4 concept lessons establish the foundation, state, setup, provider types, and the ref system. 6 features lessons build ShopWave feature by feature, authentication, products, product detail, cart, composition, and orders. 1 polish lesson added robustness, error handling, shimmer, and the 401 logout. And this final lesson reviewed, tested, and graduated the series. So the incremental build strategy worked. Each lesson built on what came before, and by lesson 10, the features composed naturally because the architecture was already sound. The provider type decision tree simplified into 4 cases. So the plain provider for read-only derived values, computed asynchronously from other providers, no mutations, no async. Notifier provider for synchronous mutable state that needs action methods. The cart is the canonical example. Async notifier provider when build method is async, you're fetching from a network or database, and Riverpod should manage the loading and error states. And the autoDispose.family combination for parameterized screens, detail screens that should clean up when the user navigates away, with the parameter determining which data to fetch. So when in doubt, is it derived? Provider. Does it mutate? Notifier provider. Does it fetch async? Async notifier provider. Does it need an argument? Add family modifier. Okay. 12 lessons down. I hope you really enjoyed the course and got to grasp and get a better understanding of Riverpod. Now take what you built or what we built, take the patterns, everything that we've talked about, go build something of your own. Thank you for building with me. See you on the next one.